When you hear the word asbestos, you probably immediately think of industrial materials, old buildings, or hazard warnings. But today, we're going to completely flip that perspective. We're going to look right past the construction sites and travel deep underground to uncover the true geological origin story of Chrysotile. We'll see how a completely natural deep earth anomaly transforms solid rock into something that can actually be spun and woven. It is a completely fascinating story of intense heat, tectonic violence, and microscopic stress. So let's start by clearing something up. Asbestos is not a single thing. It's an umbrella term for 6 distinct naturally occurring silicate minerals, all made up of long, thin, fibrous crystals. And these 6 minerals fall into 2 very different classes. On one side, you have the amphibole class, brown asbestos, blue asbestos, which forms rigid, sharp, needle-like fibers with their own distinct geological origins. Then there's our protagonist for today, the serpentine class. This class is represented entirely by one single mineral, chrysotile or white asbestos. Unlike those rigid amphibole needles, chrysotile forms incredibly flexible, rolled-up tubes. The geological process that creates chrysotile is completely unique to it, and that is the exact journey we're tracking today. Here's our roadmap. We're going to hit 4 main stops: deep mantle origins, the serpentinization process, the rolling crystal structure, and finally, the journey to the surface and the human connection. Chapter 1. Deep mantle origins. Chrysotile does not form anywhere near the Earth's surface. We have to start miles beneath our feet, in the Earth's mantle. Down there, in insanely high heat, under crushing pressure, in a completely dry environment, we have what are called ultra-basic or ultramafic rocks. Think heavy, dense stuff, peridite, dunite, originating right in the Earth's mantle. These rocks are absolutely packed with magnesium and iron, loaded with high-temperature minerals like olivine and pyroxene. And let me be clear, at this stage in their life cycle, these rocks are totally dry, completely solid, and not fibrous at all. Not even a little bit. Chapter 2. The hydrothermal catalyst and the serpentinization process. So how does this bone-dry, non-fibrous mantle rock suddenly transform into something we can weave like fabric? It takes a massive, violent geological trigger. Tectonic forces, subduction, massive faulting, literally crack the Earth's crust. These fractures open up pathways, and suddenly hot, chemically active water comes violently rushing into those dry, ultra-basic rocks. We're talking blistering hot water, somewhere between 200 and 500 degrees Celsius. This is an absolute game changer. This process has a name: serpentinization. That hydrothermal water seeps in and directly attacks the original minerals. It breaks down the olivine and pyroxene, introduces new elements like hydrogen and oxygen, and fundamentally rearranges the atoms inside. The original minerals become totally unstable and are forced to recrystallize into something entirely new. A complete and total transformation has just happened. Chapter 3. The rolling crystal and the atomic mismatch. This chemical rearrangement leads to a literal microscopic accident. When that olivine recrystallizes, it can become one of 3 different serpentine minerals: antigerite, lizardite, or chrysotile. And here's the fascinating part. All 3 share the exact same chemical composition: magnesium silicate hydroxide. Same atoms, same proportions, but the physical result is wildly different. In antigerite and lizardite, the crystal layers stack together perfectly, one on top of the other, creating soft, flat, platy sheets. But in chrysotile, the layers don't fit perfectly. One layer naturally wants to be just a tiny bit bigger than the layer right beneath it. This creates massive internal pressure, what geologists call lattice stress, right inside the crystal. And how does the mineral deal with that stress? Brilliantly. To relieve the strain, the crystal simply cannot stay flat. It curls and rolls up into a tiny microscopic scroll. Then millions upon millions of these tiny rolled tubes bundle together. And that is what creates the soft, flexible fibers of chrysotile, that we can actually see and touch. It is literally a rock that rolled itself into a thread just to stay chemically and physically stable. How wild is that? Chapter 4. Journey to the surface and the human connection. So we've got these rolled up microscopic tubes forming deep underground. How do they actually get up to the surface? The answer is a process called retrograde metamorphism. We usually think of metamorphism as rocks getting baked as they go deeper. Retrograde is the exact opposite. It's what happens when those once blisteringly hot rocks get pushed upward by tectonic forces and start to cool down. As the temperature and pressure drop, the old high-temperature minerals break down, and water-rich minerals like chrysotile become highly stable. Chrysotile heavily populates the fractures and veins as the rock rises. Now, this doesn't just happen anywhere. You find this geological setting in dramatically tectonically active mountain belts. The Pyrenees, the Alps, the Apennines, and in massive deposits in Canada and Russia. These are convergence zones where ancient tectonic collisions scraped mantle rocks miles upward toward the sky. That violent uplift fractures the rock, creating shear zones where fluids move easily, and chrysotile grows right there in the cracks and veins over millions of years. And because it formed as those flexible rolled-up scrolls, chrysotile ended up dominating human industry. We realized we could spin it and weave it. It went into corrugated cement roofing, fire barriers, brake pads, pipe insulation, floor tiles, practically everything. But here's the number that puts it all into perspective. Chrysotile accounts for a staggering 95% of all the asbestos ever used in the United States and globally. 95%. Only 5%. Only 5% was those rigid amphibole classes. Think about that. The vast, vast majority of our entire 20th century asbestos infrastructure traces directly back to that one specific serpentinization process we just walked through.